Okay, I think that the time is right, and I can introduce to the last speaker of this session, and it's Zoltan Blasik from Hungary, better to say from University of Szeged, and as well as University of Johannesburg. He will talk about coalition partitions in graphs, and Zoltan, please, the floor is yours.
Thank you very much, Istok. Thank you. And first of all, I would like to thank all the organizers on behalf of all of the participants of this nice workshop, and especially to Hamid Reza Gomamadi for the invitation. And I also would like to thank all the participants for sticking with us until the last talk. Hopefully, you will enjoy it. I'm going to talk about coalition partitions in graphs, and since we are in a domination workshop, there is no need to define all the basic notions, but I will try to give you the definitions and I will try to say some motivations in the beginning. Feel free to stop me at any point if you have any questions. Okay, so let's start with some definitions and the motivation. So in this talk, G will be a finite simple graph. And there is a huge literature of some problems which have the same kind of framework when we try to partition the vertex set of a graph into some subsets which have a specific property. For example, if we have perfect vertex coloring, then it's basically just a partition of the vertex set into independent sets. So then this is the specific property that the partition classes should be independent sets. When we are talking about domatic partition or total domatic partition, then we should partition the vertex set into two classes, which are dominating sets in the domatic partition and total dominating sets in the total dominating sets in the total domatic partition. And inspired probably by these problems, in 2020, Haynes et al. Introduced the following notions. And this will be the main notion of today's talk. So two subsets of the vertex set, A and B, form a coalition, or you might say that they are coalition partners, if none of them are dominating sets, but their union is a dominating set. So if this is the situation, then we say that they form a coalition. And we would like to find a coalition partition of a graph, which is just a vertex partition, into k non-empty partition classes, such that, and here comes a small annoying thing, that either these partition classes are singleton dominating sets. What is a singleton dominating set? Well, it's a dominating set which has only just one element. Or in other words, you can say it equivalently that it's a vertex in the graph which is universal. It is adjacent to every other vertex. So either this is the situation, and then we should put these universal vertices into their own partition classes, or the other partition classes should not be dominating sets, but the assumption is, the condition is that they must form a coalition with at least one of the other partition classes. So this is, if this can be done, then this is a coalition partition. So the first natural question is whether this exists always or not. And the situation is that even this question is not entirely trivial. And this can be proven by using the fact that every graph has a domatic partition. So a partition into dominating sets, and then there is some refinement going on, but then even then you need to think a bit more. So I won't go into the details, but nevertheless, these coalition partitions always exist. Okay, then if they exist, then the coalition number, denoted by the C of G, is just the maximum number of the partition classes in a in a coalition partition. And we can define or associate a graph, the so-called coalition graph, with to a graph with respect to a coalition partition. So if this psi is just a coalition partition of k partition classes, then the coalition graph has the vertex set which corresponds to the partition classes, and the edges will correspond to those pair of partition classes which form a coalition. So this is the coalition graph with respect to a specific coalition partition. And we say that the coalition graph is optimal if it corresponds to a coalition partition with the maximum number of classes, which is this coalition number C of G. So this is what they defined. And let me just quickly show you an example to make it easier to grasp this notion. So this is just a random graph. I just picked this one. And as you can see in the top left picture, I colored the vertices. So the color classes will be the partition classes. And as you can see, the green vertex is a universal vertex in this graph. So this should go into a separate partition class in its own. And the red partition class is not a dominating set. For example, this blue vertex is not dominated by the red ones. And the blue set is also not a dominating set because of this red vertex. So these two classes are not dominating set, but obviously if you pair them up with the green, with the red one, then they form a coalition, obviously with the universal vertex as well. I will later on say something about these universal vertices. And on the second picture, it's the same graph, but it's a different kind of partition. It's also a coalition partition. Again, for every partition class, there exists another partition class such that they form a coalition. And this is what's indicated here in the bottom right corner. So now you have 6 vertices because there are 6 partition classes, and the edges corresponds to the coalition partners. So for example, 2 and 6 are adjacent here because 2 was not a dominating set. It would dominate these vertices and 4, and 6 will be the one who dominates 5. So 2 and 6 are a dominating set, but none of them was a dominating set before. So hopefully it's clear now. And in a series of papers, actually 3 papers or maybe more, Haynes et al. Proved that this coalition number can be bounded by both from above and below with respect to the minimum degree and the maximum degree of the graph. And they determined the coalition number for paths and cycles. And they proved an interesting result, which is a bit different. It has a different flavor, that any graph can be realized as a coalition graph, which means that for any graph, there exists another graph and a specific partition such that for this second graph in this partition, the corresponding coalition graph is isomorphic to the original graph. So they proved that this can be done. And they also characterized the coalition graphs of cycles and trees. And then later on, in 2022, Bakshas, Henning, and Pradhan proved the following. So first, they characterized all graphs with minimum degree at most 1, and the coalition number equal to the number of vertices. And they also characterized all trees such that the coalition number is equal to n-1. Okay, so before continuing, let me mention that in their papers, Haynes et al. Provided many possible future lines of work, including the following. They said that what if we replace in every definition the dominating property with total dominating property? And probably that is what inspired Ali Khani, Bakshesh, and Mohammadi to introduce these total coalitions, this notion. Before going to the definitions, let me just quickly mention that since we will talk about total dominating sets from now on, we should assume that our graphs are isolate free, because otherwise, if a graph contains an isolated vertex, then it cannot have any total dominating set. So it makes sense only if we suppose that our graphs are isolate free. And the definitions will be quite similar. So two sets, subset of the vertex set, form a total coalition or their total coalition partners if none of them are total dominating sets, but their union is a total dominating set. So this is clearly the same, a similar type of definition. And we say that the graph has a total coalition partition if there is a vertex partition into k non-empty classes such that, and here comes an interesting thing, that we don't need to care about any singleton classes or anything because if a graph has a universal vertex, it's a dominating set always because it dominates every other vertex, and it should not dominate itself because it's not a requirement in a dominating set. But in a total dominating set, since we don't allow loops because we are talking about simple graphs, then there cannot be any total dominating set of size 1. So here the definition is a bit, I mean, I like this version a bit better. So every partition class must be not a total dominating set, but must form a total coalition with at least one other class. The question again, which is quite natural, that whether it exists always or not, and again, it's also not trivial, and it relies on the fact that there exists a total domatic partition in every graph, and as I mentioned earlier, so here I quite like the fact that there is no problem with universal vertices anymore. Okay, so what is the definition of the total coalition number, denoted by this TC of G? And this is just, again, the maximum number of partition classes in a total coalition partition. And the total coalition graph is, again, just the associated graph. The vertices will correspond to the partition classes again, and two vertices will be adjacent if the two appropriate partition classes are total coalition partners. Okay, and again, the total coalition graph is optimal if the corresponding total coalition partition has the maximum number of classes, this TC of G. Okay, again, just an example. This is the same graph, and on the top left, we have the same partition. And this is also a total coalition partition. And here, none of the sets are total dominating sets. And actually, any two of them form a total coalition. So the corresponding total coalition graph is just a triangle. And if you look at the second picture, it's interesting because now every vertex is a own separate color class or partition class. Why? Because if there is a universal vertex, then it dominates every other vertex, and this is not a total dominating set, but if you add all, since every other vertex is its neighbor, then if you put every other vertices into different pairwise different classes, then any one other class with this universal vertex will form a total coalition. So in this way, you can achieve the best possible, which is that the total coalition number equals to the number of vertices. But this is a special situation when we have a universal vertex, and in this situation, actually, the total coalition graph is just a star. Okay. In their paper, Ali Khani, Bakshish, and Gul Mohammadi established some results regarding this total coalition number. They also proved some general lower bounds on this total coalition number with respect to the minimum degree and the total domatic number as well. They also determined the total coalition number of paths and cycles. And they gave linear upper bounds, which we will see later on the total coalition number with respect to the maximum degree if the minimum degree is just 1 or 2. And basically, this is the point when myself, and a colleague of mine, János Barát, was introduced to this topic. And when we saw their paper, we posed to ourselves two problems. The first one is, can we give a general lower or upper bound on the total coalition number in terms of the maximum degree? So if we have no assumption on the minimum degree, then what can we say about the total coalition number? And the second problem, which was very interesting to us, is the following. If we have an optimal total coalition partitions with the maximum possible number of partition classes, then can we say something about the structure of such an optimal total coalition graph? How can it look like? Is it uniquely determined, or can we characterize them? So these questions were quite interesting to us. And in the following, I tried to say some things about these problems. Okay, so first of all, let me continue with the difficulty. So in this picture, you see the same graph again. So these two graphs are the same, not the same as the previous one, and with two different partitions. But this time, these two total coalition partitions have the same number of partition classes. And actually, later on, you will see that since this graph is a cubic graph, it's a three regular graph, then we will prove that the total coalition number in this case cannot be bigger than 6. So actually, we know that both of these total coalition partitions are optimal, but their total coalition graph, the associated graph, it's not isomorphic. So this small example shows us that maybe it's a difficult task to determine any structure of these optimal total coalition graphs. But nevertheless, let's continue. So first, I'll try to show you the known results, known lower and upper bounds in terms of the minimum degree and the maximum degree, and then our construction and the matching upper bound. So first of all, it was already observed by Ali Khani, Bakshish, and Gul Mohammadi that the maximum degree of a total coalition graph cannot be greater than the maximum degree of the original graph. And why is it that way? Well, if you take any partition class, then since it's not a total dominating set, there must exist a vertex which is not dominated by this color class, by this partition class. Or you might say that this vertex is not in the neighborhood of this partition class Ci. But we know that this partition class can form a total coalition with some other Cj classes. But in this case, if their union is a total dominating set, then it must mean that this other partition class, this C of G, I mean, one of the elements of this partition class must dominate this V sub I. So in other words, this V sub I must be in the neighborhood of this other partition class, Cj, but we know that there is at most delta of G many neighbors of this vertex. So this immediately shows us that for any partition class, there cannot be more than delta of G many neighbors of this partition class in the total collision graph. So this is a observation. And let me continue with the following one. So in the first part of our paper with János Barát, we tried to find some nice properties of the total collision graph. And the second lemma is the following. If you consider a total collision graph, then the maximum matching, the size of the maximum matching is also bounded by above by the maximum degree of the original graph. Why? Well, if it is a well-known property of any total dominating sets that the size of a total dominating set must be at least as big as the number of vertices divided by the maximum degree. Well, it's obvious. Every vertex can dominate at most delta of G many vertices. So the size of the total dominating set times delta, since it should dominate every vertex, then it must be at least as big as n. So this is a known fact. And if you have two classes which form a total coalition, then their union, which is I mean the size of the union is equal to the size of the sum of the sizes of these classes, then this should be at least n over a delta. And we also know that the sum of all, I mean the size of this partition classes altogether add up to n. So these two things together means that if you have matching, a maximum matching in this total collision graph, then since the two end vertices of each matching edge form their union, form a total coalition, and these end vertices are pairwise different because this is a matching, then it means that the size of the maximum matching cannot be bigger than delta of G. So this is another observation. And actually, from this proof, it immediately comes that whenever the size of the maximum matching in the total collision graph is equal to delta of G, with this maximum degree, then there is no room for any other partition classes, because then it would mean that for every matching edge, the size of the two end vertices should be at least n over delta, but there is delta many of them, so they must be, the size must be equal to n over delta, and it means that then this delta many matching edges uses exactly n vertices, so there is no room for any other partition classes. So in this case, the number of partition classes is equal to 2 times delta of G. Okay, so then we pose the following question to ourselves: how can we construct a graph with large total coalition number? How can such a total coalition graph look like? And our first guess would be, I guess, that we take a universal vertex in this total coalition graph, or basically a set which is almost a total dominating set. Maybe it leaves out one vertex or two. And then there should be some small partition classes which will dominate those few vertices, and then it might use many partition classes. But that's actually, it's not a good idea, because if you have a universal vertex in this total coalition graph, then it means that this is the one that forms a total coalition with every other partition classes, but we already proved that the maximum degree in this total coalition graph is at most as big as the maximum degree of the original graph. So this immediately gives an upper bound of delta plus 1 on the number of partition classes. And another idea might be that you take quite balanced partition classes, which roughly means that the size of these partition classes should be roughly the same. But then by the previous argument, since their union, if they are total coalition partners, then their union must have size at least n over delta. And if they have roughly the same size, then their union has size 2 times the size of each partition class. So from here, you get that any partition class, the size of any partition class should be at least n over 2 times delta, which again in turn gives us an upper bound of 2 delta on the number of partition classes. And you might wonder what is in between. So in between, you can think about a total coalition graph with a few almost total dominating sets, and hopefully most of them has many neighbors in this total coalition graph. But we know that any of them can have at most delta of g many neighbors in the coalition graph, and if there are many large almost total dominating sets and with many neighbors in this total coalition graph, then it would mean that the size of the maximum matching is also quite large, but it cannot be bigger than delta of g. So altogether, if everything works out, then it might be possible to reach partition classes I mean the number of partition classes to be quadratic in the maximum degree. And in contrast to this intuitive reasoning, Alikani, Bakshas, and Gomamadi proved the following upper bounds if the minimum degree is just 1 or 2. If it's 1, then the maximum cardinality of a total coalition partition is at most delta of g plus 1. And if it's equal, the minimum degree equals to 2, then it's at most 2 times the maximum degree. Okay, let me continue with our construction, which gives a quadratic lower bound. So it is possible to find a graph such that it has a total coalition partition where the number of partition classes is actually quadratic in terms of the maximum degree. And the construction works differently for if data is even and if data is odd. The even case is a bit easier, and that's why I choose to show you this picture now. So what is our graph? Well, our graph will consist of 3 parts: the top part, the middle part, and this bottom part, which contains a bunch of gadgets which are basically the same graphs. And let me emphasize here that now, since the maximum degree is an even number, so this delta of g is equal to 2 times r. So this parameter r is just delta over 2. And what is our aim? Our aim is to build r plus 1 large, almost total dominating partition classes. These will be these colored partition classes. And how can we make sure that these are not total dominating sets? Well, we make sure that we put one vertex in each of these partition classes, which is not dominated by this partition class. So that way we immediately know that these are not total dominating sets. So in the top part, we have one element from each large partition classes, and they form a complete graph on r plus 1 vertices. And And in the middle part, for every such vertex, there exists are many neighbors. Currently, they don't have a color. I will tell you shortly what will be their color or which partition class should they belong. And what is in the third part, in the lower part, in this gadget? Well, what are those gadgets? So in the gadgets, there is two sides. Let's look at the first gadget. A1 and B1 are the two sides. In A1, you have again a complete graph on r plus 1 vertices. So it's basically the same as the top part. And the B part is again the same as this top part. And you connect and you put a perfect matching between these two parts such that these edges are incident with the two vertices in both parts which belongs to the same partition class. Why is it good? Well, because since they in each of these sides in A1 and B1 these vertices are obviously dominating, and since we added these perfect matchings this way, these vertices dominate themselves also. So here in these gadget parts, every large partition class will be a total dominating set. And how many edges did we use until this point for these vertices? So a vertex in this A1 class had R many neighbors in their own class, and there is this matching edge. So we already used R plus 1 edges of these vertices. And it means that since the maximum degree of our graph should be equal to 2 times r, so we basically have r plus 1, r minus 1 many free edges. So we can use these free edges however we like, and we will connect all of these vertices by these r minus 1 free edges to the vertices in the middle part. So there are r times r plus 1, so r squared plus r many vertices here in the middle part. And that's why we need r plus 3 over 2 many gadgets, because we can dominate these vertices by using these r minus 1 free edges. Okay, so we need this many gadgets in order to dominate by every large color classes every vertex in this middle part. And then this way, all of these bottom parts, so the gadgets and the middle part, are totally dominated at this point by all of the large color classes. And only these vertices at the top, they are not dominated by any. I mean, if you fix one of the large color classes, for example, C1, then this vertex V1 dominates every other vertex in the top part, but not itself. So this is the only vertex, V1, which is not dominated by the partition class C1. And it's true for every other large color classes. So this means that these R plus 1 color classes are almost total dominating sets. And then we can introduce R square plus R many singleton color classes, because if you put every vertex in the middle part into pairwise different partition classes, then they would form a total coalition with the appropriate large partition class. So if, for example, you look at this C11 color class or partition class, then it would form a total coalition with C1, because then this would be the vertex which dominates V1, and the partition class C1 already dominated every other vertex. So hopefully it's clear now what is the construction, and it uses how many partition classes, where in this middle part every vertex has its own partition class. So it's R squared plus R partition classes here. And there is this R plus 1 large partition classes. So altogether it's R squared plus 2R plus 1, which is this lower bound, because R is equal to delta over 2. Okay, so now we proved that there exists a graph which has a total coalition partition with this many partition classes, this delta squared over 4 plus delta plus 1. Okay, and let me again emphasize that a similar kind of construction works if delta is odd. Okay, so this is the theorem. This total collision number is, there exists a graph for which this total collision number is at least this delta square over 4 plus delta plus 1, basically. But we need that delta of G should be at least 3. Why? Because when we look at this example, if R is at least 2, that is when we have actually 3 edges here, which we can use to dominate these vertices. If R is just 1, which means that delta is small, at most 2, then we have no 3 edges at this point, then the construction won't work. And then you might wonder what happens when delta is just 1 or 2. And in these situations, there exists some other graphs. Actually, K2 and C4 are 2 graphs for which the same kind of lower bound is attained. So actually, we proved that for this lower bound, for any delta, there exists a graph such that the total collision number is at least this much. And then here comes the other part of our result, that we actually prove that the same identical upper bound, the same bound is an upper bound on the total collision number for any isolate free graph. And how does this proof work? Well, suppose that we have a total collision partition with maximum number of partition classes. So this K is equal to the total collision number. Then by our previous observation, if the size of the largest matching is equal to the maximum degree of the graph, then we know that there cannot be more partition classes besides the end vertices of these delta many matching edges. So the total collision number in this case is equal to 2 times delta of G, which is not bigger than the upper bound. So suppose from now on that the size of the maximum matching in the total collision graph is actually strictly smaller than the maximum degree of a graph. And consider a maximum matching. This will be denoted by capital M, these red edges in the picture. And the number of matching edges will be denoted by little m. And then what is in these pictures? So suppose that you have these m many matching edges. Then you might wonder how many more vertices can you add to this total collision graph. And if you have a fixed matching edge, then how many common neighbors can the 2 end vertices have? If they have more than one common neighbor, then it would give rise to a larger matching. So it cannot happen. So if 2 end vertices have a common neighbor, then actually there should be just exactly one neighbor. And in this case, they cannot have more neighbors, because then again, it would mean that our current matching is not maximum one. So if 2 end vertices of a matching edge shares a common neighbor, then actually they cannot have any more neighbors in this total coalition graph. So this is not too big of an improvement. Okay, but if they don't have a common neighbor, then again they cannot have it cannot happen that both of them has some neighbors in this total coalition graph, because then again we could have chosen a larger matching. So in this situation, it might happen that out of these two end vertices, exactly one of them has some neighbors. And this is the situation in the second picture. So suppose that one of the end vertices has exactly D neighbors and the other one has no other neighbors in the total coalition graph. Then can we give some bound on this D? Well, yes, we can. And it's written down there. So how do we get these inequalities? Well, we know that this Cj partition class is not a total dominating set. It means that there exists a vertex which is not dominated by the C of G. Okay, but then since these edges are in the total coalition graph, it means that this partition class C sub J forms a total coalition with all of these partition classes. So there is exactly D plus one many partition classes. And since their union is a total dominating set, so these vertices must dominate this specific vertex. And also, if you look at all these other m-1 matching edges, these would correspond again to pair of partition classes such that they form a total coalition, which means that their union is a total dominating set again. So if you look at this vertex, which is not dominated by Cj, then this vertex should be dominated by all of these d plus 1 partition classes and the union of these n-1 matching edges. So altogether, since this vertex, which is not dominated by C of J, has at most delta of many neighbors, then the sum of m-1 plus this d plus 1 should be at most as big as is delta. And that's what's written here. And actually here, this difference, this delta of G minus M, we know that this is a positive number now because we suppose that the size of the maximum matching is now strictly smaller than delta. So actually we know that no matter how we pick eventually this M, then this upper bound on the number of neighbors here should be at least 1. Which means basically that in every matching edge, if we would like to find a total coalition graph with many vertices, then we should choose the second option and try to optimize how many matching edges should we choose, and then it would mean different upper bounds on this number D. Okay, so how many partition classes are there here? So we know that the size of the maximum matching is M. So these partition classes or the end vertices are 2M many partition classes. And now we prove that each of these end vertices must have, I mean, for every matching edge, one of the end vertices must have at most D many neighbors, and this D is upper bounded by this delta of G minus M. So we get the following upper bound. So 2 times M plus for every matching edge, M times this delta of G minus M. This is clearly an upper bound on the number of partition classes. And this is a quadratic function in M. And actually it's a downward parabola. And the two roots are 0 and delta of G plus 2. So it takes its maximum value in the middle when M is chosen to be delta of G plus 2 over 2. And this gives the upper bound, which is actually the same identical upper bound as in our lower bound construction. So these upper and lower bounds were the main results of our previous paper. And then let me just briefly show you some improvements on this. So we actually realized later on when we started to write the paper that we can prove a even stronger upper bound on the size of the maximum matching in the total coalition graph. So it was previously bounded by delta of G when delta was the maximum degree, and now we can prove that it's bounded by the minimum degree. And it's also an easier proof even. So if you pick a vertex of minimum degree, then this vertex can be dominated only through its neighbors, and the size of the neighborhood is exactly this little delta, and this would immediately gives us that the size of the maximum matching should be at most this little delta. And again, by using the similar argument, we can prove an upper bound on this total coalition number with respect to both the minimum degree and the maximum degree. And let me mention here that if delta equals to 1 and 2, then actually this upper bound is exactly giving us the same upper bounds that was proven by Alikhani, Bakshash, and Gol-Mohammadi. So the proofs have basically the same argument with this improved lemma. And yes, it's also tight. We have a construction for this one. Let me go now to the second part for optimal total coalition graphs. I think that I will need to go a bit faster on these slides. So here we ask the question, if we have an optimal total coalition graph, then and such that the total coalition number is equal to this bound, this delta square over 4 plus delta plus 1, then what can we say about the structure of an optimal total coalition graph? And actually, if you look at this upper bound proof, then you get then you get basically this whole structure theorem. So here in this top part, these are the almost total dominating classes, and these are the matching edges, these red ones, and these are the other neighbors of one of the end vertices. And actually, it's a consequence that these large color classes form total coalitions as well. So here, this part in the top part is actually a complete graph in the total coalition graph. And actually, we can prove that whenever the maximum degree is at least 6, or in the odd case it's at least 5, then there can be no edges here in the bottom part. So that's why I wrote here that this delta at least 6 is important, because that's the reason why we can prove that in these total coalition graphs there can be no edges here in the bottom part. And this is the similar situation if the maximum degree is odd. But here, if the maximum degree is odd, then you cannot take, I mean, there is two middle values for the number of maximum matching. So the number of maximum matching can be either the floor of this delta plus 2 over 2 or the ceiling. And in both situations, we can get valid solutions. So in this case, the total coalition graph is not uniquely determined, but if we fixed the size of the maximum matching, then it's also uniquely determined. And the question is, what happens if the maximum degree is at most 4? So if the maximum degree is not too big, then can it happen that these optimal total coalition graphs looks something different? Can they be different, or are they also uniquely determined? So if delta is equal to 1, it's not too interesting. Then the total coalition graph cannot be other than the complete graph on 2 vertices. So it's obviously uniquely determined. Actually, it's interesting that when delta equals to 4, then we can prove by looking at the proof of the upper bound that the total coalition graph must contain 3 stars, each of which has 2 leaves. and there can be no other edges, but actually uh, this last part, that there can be no other edges, needs some further observations, but I won't go into the details now. And the two more interesting situation is when delta equals 2. When delta equals 2, then we, by this formula, we get that the total collision number should be equal to 4. And then there must be two independent edges in the total collision graph. And we know that the maximum degree is at most 2 because the maximum degree of the original graph was 2. And these two observations means that there are only three candidates: C4, the complement of C4, and path on four vertices. And these can be realized, as you can see in the picture. So if delta equals to 2, then there can be three different non-isomorphic optimal total collision graph. And the most interesting thing is when delta equals to 3. So if delta equals to 3, since it's an odd number, you immediately have two different possibilities. One of them that the size of the maximum matching is just 2, or the size of the matching is 3. If the size of the maximum matching is 2, then you can prove that the total collision graph should be unique. It's a caterpillar. And if the maximum matching is 3, then actually have these 13 possible optimal total collision graph. And it turns out that out of these 13 possible total collision graphs, 5 of them is not realizable. And again, we have another lemma. If this total collision graph contains either a path or a cycle on 6 vertices, because in this optimal situation it must have 6 vertices, then besides these paths and cycle edges, there are some other mandatory edges. And in these examples, when you can see an X in the top right corner, these mandatory edges are not present. So that's why these cannot be realized. And some of these optimal total collision graphs, I already gave you an example, and there are some tricky ones. So here in the left side, you can see the graph with the total collision partition defined as labels. And on the right side, this is the corresponding total collision graph, and these are the remaining ones. So that's what we get on the structure of the optimal total collision graph. And let me just briefly mention the following. As I mentioned before, Hinz et al. Proved that any graph can be realized as a coalition graph, and we proved that any isolate-free graph can be realized as a total coalition graph as well. I won't go into the details, but the idea of the proof is basically we associate a vertex for every vertex of the original graph. We associate actually two vertices for every edge of the graph, and another vertex for every non-edge. So altogether, this way we use quadratic many vertices in this construction. And actually, I think it's an interesting question whether it is necessary for any graph. So can you find a graph such that although it can be realized as a total collision graph, but in the graph H, for which a specific vertex partition gives us as a total collision graph the original given graph G, then is it possible that for a specific graph G, this H graph must have quadratic many vertices? I think it's a nice problem to think. And at the last part of my talk, I would like to briefly mention some generalizations to hypergraphs. And in 2023, Michael Henning and Anders Yeo introduced an analogous concept for hypergraphs. So here again, we have a hypergraph, and two disjoint subsets form a transversal coalition if none of them are transversals, but their union is a transversal. What is a transversal? If you have a hypergraph, then you have hyperedges, and the transversal is just a subset of the vertex set which intersects every hyperedge. So this is clearly a very similar notion. And again, a transversal coalition partition is just a partition into non-empty classes such that either one of the classes are singleton transversals, which basically means that they are vertices which intersects every hyperedge, or you can say universal vertices, or the partition classes are not transversals, but they have a coalition partner. Here again, the question, does it always exist? And here the situation is that it not exists in every situation. For example, you can think that if there exists a hyperedge which is contained in all hyperedges, which means that every element of this hyperedge is actually a universal vertex. So these universal vertices must be put into pairwise different partition, singleton partition classes, and then the rest cannot intersect this hyperedge. So then it cannot happen. It cannot be defined always. But if the hypergraph is nice, then you can think about this transversal coalition number and the corresponding transversal coalition graph. I just briefly go through these definitions because hopefully you will understand what does it mean after these two other very similar examples. And Henning and Yeo proved regarding the transversal coalition number that for k at least 2, if the hypergraph is k uniform, so it means that every hyperedge has size exactly k, then this C tau of h, which is the transversal coalition number, can be bounded by k squared over 4 plus k plus 1. And this bound is again tied by they show the lower bound construction. And actually, there is a connection between total dominating sets and transversals. I'm not sure if you are familiar with this, but it's a very easy observation, observed first by Tomasi and Yeo, that if S is a total dominating set in a graph if and only if S is a transversal in the open neighborhood hypergraph of the graph. What is the open neighborhood hypergraph? Well, it has the same vertex set as your original graph, and the hyperedges will be the open neighborhoods of every vertex. And it's quite clear if you have a total dominating set in your original graph, it means that for every vertex, there exists a vertex in S, which is in the neighborhood of this vertex. And if you take the open neighborhood hypergraph, it means that this set S actually intersects every open neighborhood, which means that this is a transversal in the open neighborhood hypergraph. So by this observation, actually, this results of Henning and Yeo it can be seen as a generalization of our results. And it gives that for k at least 2, if the graph is isolate free and k regular, then the total coalition number is at most k squared over 4 plus k plus 1, which is our result because here k is equal, the graph is k regular, so delta equals k. And actually at this point, I should mention that in 2023, when I was at the 10th Slovenian Math Conference on Graph Theory in Kranjska Gora, I gave a talk about basically the same results as in the first part of today's talk. And then Michael Henning, who was the organizer of this symposia, communicated me that they managed to generalize our results and they proved their results for k-uniform hypergraphs. And then I actually, during this conference, I managed to generalize their results further and prove for any hypergraphs without the uniformity constraint. And a few weeks later, I got a message, an email from Michael Henning, and actually he gifted me the opportunity to co-supervise a student who is in the audience right now, Shahin and Jogan, and we are currently working on coalitions, total coalitions in cubic graphs So actually, I'm very, very grateful to Michael Henning because this topic and Mike gave me incredible opportunity and it opened many doors for me. So let me just quickly finish by showing the new results. So how can we generalize these results? Well, if you have a hypergraph, then for every hyperedge, this small s of f means that this is the size of the smallest hyperedge, and this capital S of f is the size of the maximum size of the hyperedge. And a very similar bound can be proven if the hypergraph is not uniform. So this small s of e and the capital S of e is not the same, then this very similar upper bound can be proven. And again, this can be improved by a similar way as in the minimum degree, maximum degree stuff. Okay, let me just omit this part. This is just about the universal vertices. And let me finish by showing you this picture. So here you can see that if one picks a graph, this is on the left side, is G, which is actually just a K12 in this point, then the middle graph denoted by H is the one which we get by applying our construction. So this graph with this specific partition has the property that the corresponding total coalition graph is exactly this one, this G. And by this observation of Thomasson and Yeo about the total dominating sets and the open neighborhood hypergraph, in the hypergraph on the right side is with this specific partition has the property that the transversal coalition graph of this hypergraph with respect to this partition is again the same graph. So actually every graph can be realized as a transversal coalition graph as well. Okay, so thank you very much. And these are my references.
Okay, thank you so much for very wonderful presentation. Any questions? We would be happy to listen your questions. Okay, it seems that there is no question. Zolta, thank you so much again, and
Thank you.
Hope so much to meet you next year in, I guess, Novosibirsk.
Yeah, thank you.
Okay, okay.